Hi everyone, I'm Sameet Agarwal, VP and GM for storage at Google Cloud. I'm super excited to be here from Sunnyvale, California. Uh, I want to spend a few minutes talking about modern storage for real-time data systems. How does cloud storage evolve so it becomes much more suitable for real-time data? Before we dive right in, I want to talk a little bit about my other job. Of course, my day job is to build storage products for Google Cloud, but my other job that I'm incredibly privileged to have is to lead the teams which build and run storage for all of Google. Uh, Google has been innovating and building distributed systems for storage pretty much since its inception. Early on, we took a bet on a storage system called GFS, which you are probably familiar with, now called Colossus. It's the storage system which pretty much underlies all of the Google products that you know, whether it's search or ads, YouTube, photos, Drive, uh, even Google Cloud. And some of the newest products like Gemini are all running on top of Colossus. Our internal systems, whether it's offline systems like BigQuery or the online data serving systems like Spanner and Bigtable, they all run on Colossus. Architecturally, Colossus is a large distributed file system, scales to exabytes of data, terabytes of throughput. Um, it's built to run both on hard drives and SSDs, and it's a single storage system. As we have been building and running storage systems for a long time, we've distilled down what we think of as some of the key attributes that we think any modern storage system should have. Uh, First and foremost, storage should form your global foundation. Uh, Not only should storage span machines, and you want to sort of think of an entire data center as a single unit of storage, but it has become increasingly important to think about storage beyond a data center to regions and an entire continent. Secondly, the notion of separation. Uh, Recently, the notion of separating compute from storage so you can elastically scale compute and storage and not have to tie them together is been very common and standard across the industry. But equally important is the notion of performance and storage separation. You want to be able to store a bunch of bytes, but then mix hot, warm, and cold workloads in the same storage system. This allows the storage system to be used optimally and get the maximum efficiency out of the storage system. Third is a single consistent stack. We found it very important to have a single consistent API across all of the workloads. Uh, Applications don't have to deal with the complexity and the variation of different kinds of APIs and different kinds of semantics uh, while changing the application characteristics around performance and reliability. Lastly, management. It's very important that the cost of managing the system does not scale linearly with the amount of storage. As the amount of storage grows, the cost of management cannot grow linearly with it. Okay, so now let's talk about how some of these attributes show up in the cloud, especially as storage becomes more real time. One of the first modern storage systems that showed up in the cloud was in the early 2000s with Amazon S3. Early on, storage in the cloud was primarily targeted towards offline and really offline systems like backup and cold storage. Over time, people realize it's a great storage system for websites, image video storage, generally content storage and distribution workloads. Because in many of these cases, the actual data was served out of CDNs, and users needed a much lower performance but much more scalable storage system to host the data. In the last few years, the use of cloud storage as the backing store for batch data applications like analytics and AI data prep has become a lot more common. You see the rise of cloud data warehouses and cloud data lake systems over the last few years, which primarily are built on top of cloud storage. The next phase in this journey is to think about real time data. When you think about modern databases like Aerospike, stream processing systems like Confluent and Kafka, AI training and serving jobs which need low latency and very high performance. or HPC systems, how do we make cloud storage be a suitable store for real time data? So, before we jump into real time systems, let's look back a little bit at the analytics journey. The notion of building a single data lake or a single data warehouse, which can store all kinds of workloads and all kinds of data in a single repository, have a single unified table format which can satisfy all of the kinds of data, build consistent security and governance for all the data. This has become a de facto standard across all companies. I would argue cloud storage is the ideal storage for the data lakehouse. First and foremost, with its enormous scale, it can act as a single source of truth for all structured and semi structured data. So it's a single data repository, makes management easier, and you have to deal with only one copy of the data. From a reliability point of view, cloud storage promises incredible durability where you have no risk of losing your data. Built-in fault tolerance, so your data is always available and secure. Uh, Equally important is performance. Um, with cloud storage, you can get incredible amounts of throughput, up to hundreds of terabits of bandwidth, unlimited scale in terms of storage. With this level of scale and this level of storage, it's really important to be able to manage cost really well. Cloud storage provides you tools to manage your data between hot and cold appropriately so you can control your costs. Cloud storage also has a very rich ecosystem of integrating to open source frameworks, works with ISVs and third party data platforms, and our own first party solutions like BigQuery and Dataproc and Dataflow. Uh, it provides a simple, single, consistent API for all the data, so you don't have to worry about sort of different kinds of data. Cloud storage also provides a rich set of tools and capabilities to both control access to the data and also provide end-to-end provenance of where the data came from and what the source of the data was. So as we start thinking of the next phase of this journey and look at cloud storage moving to real-time data, real-time brings with it its own set of complexities. You have a bunch of different types of storage with different performance characteristics, different interfaces that are needed for real-time systems, and you may want to place your data closer to where the application is for performance reasons. In all of these cases, you end up with multiple copies of the data. Some of the simplicity with the data lake house gets lost because now you have the risk of the data being out of sync or unavailable. And with multiple copies of the data, there is the risk of inconsistent security models and having data being accessed by people who should not have access to it. In a nutshell, moving from batch processing to real time brings increased cost and complexity. So, as we look at the journey of the data lake house to real time, we think of its evolution from a data lake house to an AI lake house. We want the data AI lake house to be a single source of truth, not just for structured and semi structured data, but also unstructured data. Very important is latency. You want not just very, very large amount of throughput and bandwidth, but very, very low latency to access the data, and a very large scale, not just for data access, but for metadata access. Uh, Real-time systems come with their own frameworks and own APIs, including File API, and you want to extend uh, the storage system to have these frameworks as well. And there is ever increased concern with a lot more data around the security and governance of this data. So we think of our evolution of cloud storage to slowly become the cloud AI storage. The vision for cloud AI storage is very simple. First and foremost, you want to store your data only once. Uh, Store it once, manage it once. Logically, it's just one copy of the data. But then we want to be able to give you access to the data anywhere in any location with any performance level that you want across a wide variety of APIs and interfaces and with unlimited scale. Let's look at cloud AI storage a little bit under the hood and see how it's really implemented. At the bottom of the stack, is your familiar cloud storage. This is the infinite scale repository for all your data, which acts as a single source of truth and single source of management. It's a place where all the data can be landed. On top of cloud storage, you have a series of different kinds of caches. These caches provide performance acceleration, so you can get access to your data with whatever performance you want. But they also help bridge and integrate with the different APIs that sit on top. Cloud AI storage has a collection of APIs and integrated into the most popular open source APIs and frameworks, whether it's a Hadoop and Spark API, PyTorch and JAX and TensorFlow for AI. Cloud AI storage can then easily sit under a variety of data processing systems, whether it's BigQuery, Dataflow, Dataproc, as Google's own analytics engines, open source systems like Hadoop, or third-party ISVs like Databricks and Snowflake. And we have a rich ML platform sitting on top, which with Vertex AI as Google's own AI platform or customer-built AI platforms. All of this data is then uniformly accessible through common identity and access, intelligent data management, and a catalog. Uh, let's spend a few minutes looking at one particular aspect of cloud AI storage, the vision around storing once and being able to run anywhere. I will give you a couple of examples. We have a customer who's a national retailer. They have buckets with petabytes of data. They have many internal users who are spread all over the country, and they need to run data intensive workloads. These workloads need to run in specific cloud regions because of proximity to the users and proximity to other applications. Latency is super important for these applications, and they need to run in particular regions. We also have a large social media platform that has many users running daily ML training jobs that run over petabytes of data. In this case, they need access to the latest GPUs and TPUs. In this climate and in this environment, these GPUs and TPUs are hard to come by, and they have availability only in certain regions of Google Cloud. As you can see in both of these examples, the customers have requirements to run their compute in particular regions where the data may not be available. Now, there are a few different choices. Either the customer can move the data around to wherever the compute is and make copies of the data. Moving data around is clearly expensive, not just from an infrastructure point of view, but also from a human labor point of view, and it's also time consuming. There is a risk with these many copies of the data that some computation is running over stale data and does not have the latest copy of the data. The other alternative the customer has is to leave the data in one place and just access it over the network. This will, of course, introduce latencies in the compute jobs, and there will be additional cost of transferring the data over the network every time it's accessed. Lastly, it is very possible that you may not know a priori what is the data to move and where to move it. So somehow the administrator has to have knowledge about what data will be required where. So when any of our customers use cloud storage, one of the first choices they have to make is where do you store your data? The most common choice, and it's a choice that is available in all the clouds, is the notion of creating a bucket in a region of the cloud. This is the lowest cost option, and it's pretty straightforward. You pick the region where you want the data to be and you store it there. A more flexible option that Google Cloud provides is the notion of a dual region. A dual region is where Google Cloud will automatically store and replicate your data to two regions. The data is consistently available in both of the regions, and it provides more flexibility than a regional solution. So in this case, the compute can run on either of the two locations and have access to all the data. The third option, which is a unique option only in Google Cloud, is the notion of a multi-region. A multi-region is typically a continent like a US or Europe, where the data can be stored anywhere in that continent. It's the most flexible and automatically provides disaster recovery protection by making sure the data is spread across at least two regions. The data is then accessible on any of the regions in that continent. So it's the most flexible option. The one downside with multi-region storage is there may be long network latencies when the data is accessed because the data may not be in the same region as the compute is running. So recently, we're very excited to launch a new feature, the first of its kind in any of the clouds, called Anywhere Cache. Anywhere Cache, when combined with multi-region buckets, is the one that truly makes it possible for you to store your data once and run it anywhere within a continent. The idea of Anywhere Cache is very simple. The data gets stored in an underlying storage bucket, which is a multi-regional storage bucket. And then you can go to each of the zones in any of the regions in that continent and turn on Anywhere Cache. It's a very simple setting at the bucket level. No provisioning is required. Whenever an application tries to access the data, it'll automatically get cached in that zone in an SSD based local cache. That cache automatically scales to the amount of data that needs to be cached with no provisioning upfront required. And the cache is truly transparent. It works with existing APIs and existing buckets. No changes to the applications are required. And every access is consistent with both with respect to the data and with respect to security. So it's entirely consistent as if you read the data from the underlying bucket. So with Anywhere Cache, you get what you want. You get fast time to get answers, and you can efficiently use the compute wherever it is. So whether it's CPU, you want to run compute in different regions, or GPUs and TPUs, you can locate your compute wherever you want and get access to the data quickly. This scales to very large data sets. You can get up to petabytes of data in the cache. And this can dramatically lower your cost because you only pay for what you use, not copy all the data. And you can avoid network egress charges if you're trying to access it remotely. There is no serving of stale data, so it's fully strongly consistent. So it's as if everybody has access to the same single copy of the data. And it's a very simple solution. No application changes are required. So this is a way where cloud storage is evolving to meet the requirements of low latency computation, but at the same time give you the simplicity and ease of use of a single copy of the data and a single giant infinite data lake. Uh, this was just one of the examples of the kinds of things we are thinking of and implementing as we take this journey to evolve cloud storage to become more suitable for real-time data. I'm very excited about what the future holds and how we can continue evolving to create the modern storage platform for the future real-time databases. Um, I'm excited and looking forward to the kinds of applications and real-time data systems that will be built, taking advantage of some of these capabilities coming in. The modern storage for real-time data is coming, and I'm looking forward to the future. Thank you, everyone.